Okay, welcome back to my programming and ARM assembly video series. And in this video series, I'm working on a general purpose integer to ASCII conversion function. Now, when I left off in the last video, I was doing a quick test to make sure that the code as it stands so far does not get stuck in an infinite loop and doesn't segfault. But we haven't actually shown that the code produces the result that we're looking for. So let's go ahead now and let's edit our main file. And what we can do is right after we return from the integer to ASCII call, we can immediately do a branch and link to the print function that I created in a previous video, because we know that according to what we have defined in the integer to ASCII, like the way we've defined the way it works, is that when it comes back, R1 will be pointing to the memory address for this work that we've done, where we've worked on this conversion. And that works out really well, because in order for the print function that we created to work properly, it needs to have register 1 preloaded with the memory address of the string that it wants to print. So it works out really well. However, it occurs to me that there's a potential issue here. But let me go ahead and make the code first and show you what's going to happen. We're sending 1, 2, 3, 4 over to the integer to ASCII conversion function. It's doing that conversion by going to this memory address that we've allocated, and it's replacing these zeros, and I'll talk more about that in a moment. But it's replacing this 0 with the number 1, this 0 with the number 2, this 0 with the number 3, and this 0 with the number 4. And then it's replacing this 0 with the null byte. But the problem is currently is that we then advance, and each time we do that, we advance the memory pointer forward by 1. So when we come back, the memory pointer is actually still pointing to this address and not this address. So when we run this function, what we're going to have happen is we're going to get a string of zeros instead of the 1, 2, 3, 4. And it occurred to me that the easiest way to fix this is by so a lot of times when I come into these functions, I want to, we always need to push some registers onto the stack and then pop some off. But depending on the situation, if we're writing changes to a certain register in the middle of this function, we don't want to pop that register off the stack when we exit, because we will essentially erase all the changes that we've done. But in this particular case, since register 1 just contains a memory address, we actually want to pop that register back off the stack right before we leave, because that's going to have the net effect of rewinding that memory pointer back to the beginning, which works out in our case. That's what we want to do. So now if we remake the code and run it, we should get 1, 2, 3, 4 like we would expect, and we do. So let me talk now about this whole 0 thing. Why did I do that? The easiest way to illustrate that is going to be by creating another variable. I'm just going to call it message, and we're just going to say thank you, and that's going to be it. So as soon as we print that number, then I'm going to say load into register 1 the memory address of message, and then branch and link to our print function. I'm going to do one more thing though. I'm going to go ahead and put in this NL variable, which I'm going to say stands for new line. And then we're going to have a new line. So after we print the number, I'm going to say load into register 1 the memory address of new line, and then branch and link to the print. That way, after we print the number, it'll give us a new line. And I don't want to have that new line embedded into the integer to ASCII conversion, because there's going to be many instances where you don't want your number to have a new line after it. You could imagine, like, if you wanted to say, like if you're playing a game and you have 10 gold coins, you don't want it to say you have 10 new line gold coins. You want it to say you have 10 gold coins all in the same line. So if we were to embed a new line at the end of the number, it would do something like that. It would be like, you have 10 new line gold coins, and it would just mess up the flow. So we don't want to impose that onto the integer to ASCII conversion function. All right, so let's go ahead and take a look at what we have now. Let me make and clear, and we should just get 1, 2, 3, 4 new line, thank you. And we do. So what happens if we just allocated, or if we just essentially initialized this num variable as quote quote, maybe even pause the video and think about what would happen. But I'm gonna go ahead and write that out, make the save those changes, make the code, and rerun this. And we get 1, 2, 3, 4, new line, 2, 3, 4. So let me explain what's happening here. Essentially when this program gets assembled, linked, and the underlying kernel runs this program and allocates memory space, let's imagine that this memory space that was allocated right here is memory space 1. And the only thing that got put into this memory space is the null the null byte, which we can't actually see, but the ASCII's type included a null byte here. So let's pretend that this is memory space 1. The very next thing that we declared here was this message. So that got into memory. The T is memory space 2, and then this is 3, 4, 5, 6, and so on. So you can probably see where I'm going with this. So when we call into the I2A function and we pass in 1, 2, 3, 4 to be converted, the memory address that's being pointed to is this memory address right here, like 1. So this null byte gets replaced with the number 1, and then the immediate next memory space 2, is this letter T. It gets replaced with the number 2. Then the H gets replaced with 3. The A gets replaced with 4. And then the letter I, or the letter N, gets replaced with the null byte. So if you think about what happened when we looked at the outputs, let's go ahead and look at that again. Let me quit and not save because I don't want to save that. That's exactly what we see. We get 1, which was the memory space of num, and then it basically bled over into the thank you message, and it printed 2, 3, 4. Then it printed new line, and then it went back into the thank you message, which was overwritten with 2, 3, 4 null byte. So that's what's going on there. So that was the reason why I included all those zeros in this num variable, so that we can account for the longest possible memory space that we need to accommodate for a number that is up to the billion range. The largest possible number that you can have in a 32-bit unsigned integer is like 4.2 billion something. So that means we need 10 zeros worth of space essentially. But we may also want to, we do also want to account for the possibility of wanting to show a negative number. So that means we need an 11th character to represent that negative number. And there's also this possibility that, what if we wanted to upgrade this function in the future? Suppose we wanted to say, in addition to passing in register 0 and 1, we also want to pass in register 2 with a binary value, or a Boolean value essentially, that's either 1 or 0. And if it's 0, it's just going to behave the way it's behaving right now. But if we pass in the number 1, then when we get back our number, we want it to include commas. So we might want to say negative 1,200,300,000,099. And that, so if when we go into this I2A function, if register 2 contains 1, then we also want to return our value with zeros. That's just a possibility. I'm not actually going to take the time to do that now, but perhaps in the future that's an upgrade we can consider. So that would mean that in addition to our 10 characters that we need to represent numbers in the billions, and the 11th character that we would need for the negative sign, we would also need a 12, 13, and 14th character for those commas. So that's just something to consider. But for now, I'm going to say, let's have 5 zeros here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I meant to say 15, not 5. So let's say we'll have 15 zeros there. which will make sure that no matter what number we get back from I to A, we are definitely not going to worry about bleeding over into the next variable. Okay, so let's go ahead and write that out. There's another thing that I want to deal with before we close out this I to A function, and that's negative numbers. Currently, we're not dealing with negative numbers, so let's go ahead and add in some code for that. So similar to what I did with the ASCII to integer conversion, I'm going to move into register 7 the immediate value 1, and before I forget, that means I want to update that and update that. And this number 1 here is either going to be 1 or negative 1. And the default case will be a positive 1 because we're just going to assume the default case is a positive number. But as soon as before we go into the loops, we're going to compare register 0, which is the register that contains the integer to be converted, either register 0 or 4 because we made a backup of it there. But we're going to compare register 4 with the immediate value 0. And we're going to say if register 0 or 4 is less than 0, then branch to this new label that I'm going to call negative value. And if that's not the case, if it's not less than 0, so if it's 0 or higher, then just go ahead and do an unconditional branch to loop 1 like like we were doing before. So let's create this negative value label. And what we want to do here is we want to move into register 7 the immediate value negative 1. And then what I'm going to do is I'm actually just going to multiply our register 4, which is the register that contains the copy of register 0. I'm going to multiply that by negative 1, which is just going to have the net effect of making that number positive. And that might seem weird if I'm having a negative number. Why do I want to make it positive? Well, the reason I want to make it positive is just so that my loops can handle it as if it were a positive number. And the only difference between, in terms of the way we view it, the only difference between a negative number and a positive number is that it has a minus sign on the front of it. So if we are dealing with a negative number, we're going to make it positive, but we're going to move into register 5 the immediate value of the negative sign, and then we're going to store a byte in register. We're going to store the byte that we just got into register 1, which is the memory address that we're writing to, and then we're going to advance that forward by 1. So if the number is negative 123, we're going to come in here, we're just going to say make it positive 123, but then add a negative sign onto the beginning of our output. And then as we go forward here, we're just going to deal with it as if it's a positive number. Now, after we finish loop 1, we have essentially lost the information that we had in register 4 to begin with, and that's why we're copying register 0 back into register 4. But when we do that here, we're copying the original number, which is potentially still negative. So what we want to do here is we want to do this multiplication again, where we reconvert register 4. Once again, we convert it back into a positive number so that loop 2 doesn't have any problem dealing with it. All right, so let's go ahead and write that change. Let's quit. Let's edit our main.s file that represents our driver code. And let's put in a negative number here. Start with negative 1, why not? And let's write this out. Let's quit. Let's make our changes, clear the screen, and let's run this and see what we get. Okay, so we're getting our negative number. So that's looking good. Let's go ahead and just make a few tests here to make sure that there aren't any weird edge cases. So let's check for, let's check negative 0. Curious what happens if we do something like that. Of course, there is no such thing as negative 0, but let's just see what happens. Okay, so we get 0 like we would expect. So we tried negative 0, we tried negative 1. Let's try negative, I could see 10, 100, 1,000, stuff like that. Let's make our code, clear the screen, and let's run. And yeah, here we have an issue, and we're getting the colon, and I bet I know why. Here, let's see. So we're doing this, and go into loop 1, I will bet that 10, yeah, we're doing strictly greater than, and we probably need greater than or equal, greater than or equal, greater than or equal. I think I made that same mistake in the previous, in the ASCII to integer. I suspect that's the problem. Let me save that and rerun. Yeah. Okay, so let me also check, just to be confident, check like negative 100 and stuff like that. And let's also try negative 9, negative 11. Let me clear this out. Negative 9 is fine. I just want to check those values that are kind of around those, you know, when you're doing greater than or equal, you want to check equal to, you want to check the number just below it, the number just above it, just to make sure that you're not making any, missing anything there. So let's try 11. And that's working. Okay, so I feel like that pretty well takes care of that function. So let me just quickly do a review of what we have in here. Make sure I didn't leave any comments or have any strange formatting someplace. So that looks correct, and I don't see any problems with comments or anything. So let me just run one or two more tests before we call it good. And let's do like I was talking about earlier, like if you're playing like a dungeon game of some kind, and we'll say you have, and then the gold 2 message will be gold pieces, like that. And then we'll say you have, and then the number will be like 101. So when we come into this program, we want to load into register 1 the immediate value or the memory address of gold 1, and then we want to branch and link to the print function. Then we want to calculate our gold, and then when we come back, we print the number. We don't want the new line here just yet, so we'll say load into register 1 the memory address of our gold 2 message, and then branch and link to the print function at that point. And we'll just put the new line message on the end of that, and we won't worry about these other two. We'll say we're done with these for now. And so we'll get rid of these. And so let's see what we have. And you have 101 gold pieces. So this is an example of, you know, why I don't want to embed a new line right at the end of that ASCII integer to ASCII conversion, because otherwise, like I said, it would be like you have 101 and then gold pieces would be on the next line, which isn't something that you'd want. All right, so I feel pretty good about the state of this integer to ASCII conversion function. So I'm gonna go ahead and say that we're done. I'm gonna call it a win and move on with what we have coming up in the next series. If you made it all the way to the end of the video, thank you so much for watching, and I hope to see you next time.